Hello everybody, welcome back to another glorious maths video. In this video, I'm going to be making a few remarks on quotient rings because I was making a video for the abstract algebra series and then I realised that I hadn't actually introduced quotient rings, so let me just get some light in here. Hello. So I'm just going to do a quick few remarks so that when I actually use quotient rings from now on, you'll know what I'm talking about. Anyway, so the first thing to notice is that given a homomorphism, a ring homomorphism, F, between any two rings, the kernel of F is an ideal. And the reason for this is, well, if A and B are in the kernel of F, then F of A minus B is equal to 0, so A minus B is in the kernel of F. This should be pretty obvious, and then because F of A minus B is just F of A minus F of B, and if A is in the kernel of F and R is in R, then F of AR is equal to 0, F of R is equal to 0, which implies that R times A is in the kernel of F. Alright, so this is a little bit of motivation, and now we're going to use ideals to generate a ring. And so a nice example of this is the integers mod n. So notice that the integers mod n, I'll just write it like this for short, is a ring with operations that I'll show in a sec, containing integers of the form n times a, n times a plus 1, up until n, like this basically. So multiples of n plus 1, and so forth up until n minus 1. Now, the integers mod n forms a ring with R plus n plus s plus the principal ideal of n is equal to R plus s plus n, and similarly multiplication is defined as being Rs plus n. So, this is clearly a ring, you can check that for yourself. And there is a natural homomorphism between the integers and the integers mod n, which maps n, let's just use R for now. R maps to R plus n. And now we see that the kernel of this homomorphism is precisely equal to the ideal, this principal ideal of the multiples of n. So now we're going to use this example right here of constructing a ring like that in order to generalize it. So, first of all, given a ring R and ideal I in R, we have that A plus I. So, in this case, R will be the integers and the ideal I will be the multiples of n. So now, in this case, I is just this right here, and A is going to be an element of the integers. and this is equal to the set of all a plus x, such that x is in I. Alright, and now, so in this context here, it's going to be some integer a plus all the multiples of n. Now, again, this forms a group, so so the set, let's say the set of all a plus I with a an element of the ring forms the ring itself, denoted R mod I. I'll denote it like this because we've already done field extensions, so it might get a little bit confusing. I actually don't remember if the slash is a different way around for field and ring extensions, but I'm just going to write it like this just in case, just to avoid any confusion. With respect to the operations R plus I plus S plus I is equal to R plus S plus I. Same here. And again, R plus I times S plus I is equal to RS plus I. Now, again, there's a natural inclusion, let's call it alpha, between, there's a natural homomorphism, let's say, between R and R mod I, which maps R to R plus I, and again, the kernel of alpha is equal to I. So it's this ideal I. And so, here, we've generalized this idea of creating a ring from the integers mod n, to generally having a ring, an arbitrary ring R and an ideal I in R, and we kind of use the cosets. So in group theory we use cosets in order to form a group with the operations GH, G prime H equals G prime H, for example. So how coset multiplication is defined like that. Analogously in ring theory, this can kind of be thought of as the cosets, and the ideal can be thought of as like the normal subgroup, and we get like this. Now, there is, since these are just a few remarks, I'm just going to finish off with one last connection to number theory. So, when are the integers mod n a field and not just a ring, for example? Theorem. The integers mod n are a field if and only if n is prime. Right, so let's show that if n is prime, it's field. So, proof. We'll do this implication by contradiction. So assume n is equal to some r times s, where r, s are not equal to 1 or n, so they're between 1 and n, and they're integers. Then we would have that r plus n is not equal to 0. S plus n similarly is not equal to 0. But r plus n times s plus n is equal to n plus n is equal to 0 plus n. And this is the 0 element in the ring. And so we would have 0 divisors. But we don't want 0 divisors. That can't be a field. Now, let's do the other implication. So the other way around. How do we do this? Well, again, assume that the integers mod p, I'll use p because that's a nicer version of writing a prime, aren't a field. Alright? Then, if R plus P times S plus P equals 0 plus P, then this right here means that P divides RS, and therefore by Euclid's, I'll just say by Euclid, we have that P divides R or P divides S. Alright? But therefore, this would mean that one of these is 0. And therefore, R plus P equals 0 plus P, or and so one of these must be a zero divisor, and by the fact that every finite integral domain is a field, this completes the proof, because it's a contradiction again. Alright, so this is a few remarks about quotient rings, because I believe that I forgot to actually make a video on them or include them in any of the other videos. So, yeah. Until the next video, goodbye!